Hello and welcome to Dinis Guarda YouTube podcast show. Once again, portraying and profiling some of the most influential personalities in technology and business in the world. During this series, where we interview over 350 personalities in the world of technology and business, we always aim to get the best people, the best storytellers, the best case studies, and special people that are changing the world. So today we have actually one of these people that is changing the world in multiple layers, and as well someone that works for the presently biggest company in the planet, NVIDIA. So I welcome to our series someone that has a fantastic CV, but as well someone that is changing everything we're doing. So I welcome Rev Lebaredian, the Vice President of Omniverse and Simulation Technology at NVIDIA. So Rev is a technologist, entrepreneur, and business leader. He's the Vice President of Omniverse and Simulation Technology at NVIDIA, where he leads the Omniverse product, engineering, and research teams. For the last 5 years in particular, Rev and his teams have been combining the rendering, physics, simulation, and artificial intelligence technologies pioneered by NVIDIA into a single platform for creating and simulating physical, accurate virtual worlds, the NVIDIA Omniverse. NVIDIA Omniverse is a platform of APIs, SDKs, and service that enables developers to easily integrate universal scene description and NVIDIA RTX. So in a nutshell, the physical and the digital with AI tools and technology. Rev has a fantastic CV that brought him for starting in Hollywood, working with Warner Brothers and Disney Dream Quest Images. And then he had his own venture, Steamboat Software. And after that, he actually has been in NVIDIA for 22 years as we speak. And Rev, of course, is known as well for rendering the volumetric algorithms of top VFX studios around the world in popular films like Stuart Little, Dr. Seuss, How the Grinch Stole Christmas, X-Men 2, and many others. Some of the achievements that Rev has been doing is bringing the physical and digital world a lot of innovation, a lot of research and development, and as well fantastic areas that combines the physical and robotic world that we live in and the artificial intelligence inception technologies. So very excited to continue with our fantastic interviews. And today I'm particularly over excited because there's welcome to our series, someone that combines, I would say, a lot of the fantastic capacities of our times. That is the creativity, the technology, and as well a fantastic CV that speaks, we could actually speak for hours here. So I'm particularly excited because we are bringing multiple different worlds of simulation technologies, AI, and as well, of course, a personality from NVIDIA, but as well a personality from the world of film and special effects that will be talking about all the things that are happening when we speak about technology. So Rev Lebaredian, sorry for my spelling. And so Rev, I will go straight away to a bit of your personal background. So I would say your profile is amazing in multiple levels, and of course now you represent one of the biggest corporations. But before, you've been working with the biggest Hollywood studios from Warner Brothers, Disney Dream Quest, and now you are in NVIDIA. And as well, for people listening to us, you are part of many popular films like Stuart Little, Dr. Seuss, and a lot of others. So to start, so what was the thing on your education or the moment that made you realize that this is the thing you wanted to do, or one or two moments that you thought that it was there, and what was a person or something like that, or a moment that made you realize all these new possibilities?
For me, it actually goes way back, even before education. I was very fortunate. My father, in the early 80s, he bought me a computer when I was 6 years old, which is a very strange thing to do. This is in 1980, 1981. Most people didn't have computers, let alone 6-year-olds. But I fell in love with it. The idea that I could instruct this machine to do whatever I ask it to do, as long as I could figure out how to ask it correctly, was fascinating to me. Years later, 4 or 5 years later, I came across an image inside a computer magazine. I had a Commodore computer. That was my first computer. It was a Commodore VIC-20, then a Commodore 64. Then there's this new computer that had come out called the Commodore Amiga. And this this Amiga had a lot of computer graphics capabilities. It had 4096 colors, and it could do animation. It could do a lot of these amazing things. So I was reading in this magazine about the computer and its capabilities, and there was an article that had an image of two balls, two spheres floating over a checkerboard floor. And I was just amazed by this image. I couldn't understand what it was. When I read the article, it was clear to me that, or what they clarified was that this image was generated by a computer program. It wasn't drawn and it wasn't a photograph. It was something that looked kind of real, but it wasn't hand painted. And when I realized the computer program made the image, I was sold. I said, "This is what I'm going to do for the rest of my life," because I always wanted to make images, but I couldn't draw naturally, like much of my family. But I knew how to program a computer, so I set about learning how to do this for the next 7-8 years or so, until I became legally an adult. 1993. That was a very special year. It was the year that NVIDIA was born. It was the year the World Wide Web was born. So essentially the beginning of the internet. It was also the year Jurassic Park came out. And Jurassic Park was a very seminal moment for 3D computer graphics, because up until that point, it had been largely kind of this niche hobby thing and maybe used a little bit. But Jurassic Park, when people saw those dinosaurs walking by their screens for the first time, it was clear there was no going back to the old way of doing visual effects. And so this 3D computer graphics thing that I'd been working on for years, or just doing it on the side, all of a sudden had a market. And I happened to be lucky in that I was born and raised in Los Angeles, which was the epicenter of this. So I managed to, at 18, get a job that I probably if it was 5 years later, I would not be able to get. But because there was such high demand for people that knew anything about computer graphics, especially engineers who could program this stuff, I got a job at Warner Brothers, working on a project to make 3D computer graphics look like they were hand drawn cartoons, the Marvin the Martian in 3D for a stereoscopic film. And then the next big project was at Disney DreamQuest. I worked on a movie called Mighty Joe Young, where I built the system to do fur and hair for the gorilla, which was the main character in the movie. And I developed a renderer to essentially simulate how that fur and hair would look in real life. I was very young then. I was 20 years old, and I would never be able to get that job today. But then they were desperate, and so managed to solve that problem for them for that time. We got nominated for an Academy Award. And then soon after, I started my own little company where I developed a new renderer that did much more than fur. It also did volumetrics and other things for things like smoke and fire and these kinds of effects, which were very hard at the time to do. They're still pretty hard to do. And I licensed that to many of the big studios until NVIDIA called me one day, and I moved on to the next stage.
Oh, that's spectacular. How your passion drove you from almost childhood to make the think of dreams, like they say in Hollywood, but as well all over the world. So I want to just come back to your childhood. So do you think that, and I think especially for young people listening to us, it was your passion or your father that gave you the computer had a role on that, or was a mix of both? I would like to touch, because now there's a lot of drama around AI, and of course we'll have more drama, but I want to have a bit of more the storytelling on that.
You know, this is a question that I get asked quite often, and I think about, like, what is it? I think it's a combination of both. You know, the reason my father bought me that computer, I had done apparently very well in the state tests that they gave to all students. I was in first grade, and they wanted to skip me 2 grades to third grade. And my father was concerned that, I would be so young in a class with those that were older, so much older than me. I was even young in the class I was in, so it'd be almost 3 years difference. And so he asked some friends. He had a child psychologist friend. He said, "Should he do this? Should they skip me or not?" And he suggested that since I seem to be interested in things that are scientific, math and science, to just buy me a bunch of toys related to this. So he bought me a microscope and a telescope and a chemistry set, and then finally the computer. The computer was the one that kind of stuck. I liked the other things, but this was special for me. As I was growing up, I knew I wanted to do this, but I didn't know I wanted to do it as a career. It was just like something that was interesting to me. Uh, I also had other interests. When I got older, I was studying political science and history and other things that were also interesting. If I had a few more lifetimes, I think I would go probably do political science, maybe economics, some other things that are also equally interesting to me. But the opportunities presented themselves. That year, 1993, was a critical one. The stars kind of aligned. I was in the right place at the right time, and I happened to have skills that were needed. So what I tell young people when they ask me, I get asked a lot now at universities when I speak, and by parents who are asking about their children, what should they do? Uh, a lot of people will give you the advice to go follow your passion. I think that's actually really bad advice, because I think 18-year-olds just entering college have no idea what they're going to be passionate about. I tell them to go follow their skills. If you happen to be kind of good at something and you have some skills in areas in some place, go follow that and see if you can go apply it to some place where it will be useful. Even if you're not passionate about it now, you will become passionate once you see that you can make an impact. Just the sheer joy of being good at something is enough to stoke passion. Usually 18-year-olds are passionate about things that they consume, not things that they make. They might like video games, they might like movies, or being an influencer on YouTube or something like that. But the making of the thing is usually not the same as consuming it. Just because you like playing a video game doesn't mean you're going to like making them. It's better to go focus on the things you're good at making, the things that you're good at building, and then become passionate about that rather than the other way around.
I love it. And it's a fantastic, inspiring advice for young people listening to us. So your profile is quite amazing, because you literally had like 5 jobs in your life. And from these 5 jobs, at least 4 of them were in simultaneous, more or less. So I just want to touch for people listening to us. And of course, we'll put all this information, whatever you are listening from us. But you were from, like you mentioned, senior software engineer at Disney to Atomic Cow CTO, then president CTO at Steamboat Software, and then advisory board member of the Tumo Center for Creative Technologies. And in January 2002, you got into NVIDIA, and you've been there for 22 years and 11 months. So congratulations. So tell us a bit about this trajectory, because it's not something, first of all, most of the corporate jobs, 22 years, quite an achievement, but as well, during 22 years, NVIDIA became the most, or the biggest by assets company in the world. And as well, of course, made a revolution in anything we do in terms of AI. So from starting with software engineering for special effects in Hollywood to be in an AI company. So tell us a bit that trajectory.
Yeah, it is quite strange. And if you had asked my 20s self, where I would be 20, 25 years later, I would have never guessed that I would be at working for the largest company in the world and actually be e-staff. I work for Jensen as part of e-staff directly. This was definitely not a plan or something I even aspired to be. I was happy just doing my own thing with my own little companies. But I followed the thing that I was interested in doing, things that excited me. I love computer graphics. I loved doing 3D simulation to create those images. And I I was happy actually with my own company, Steamboat Software, writing my software and licensing it to these studios, and I was going to continue doing that. Making movies was cool, but what was really exciting to me was the actual software, the engineering part of this, and building these tools and making others successful in their endeavors, making tools for others. When NVIDIA called me, I actually wasn't looking to go work for NVIDIA or anywhere else. I was happy just doing my own thing. But months earlier, I was at a big conference for computer graphics. It's called SIGGRAPH. It's a yearly conference, and I was at a dinner with other engineers and researchers who develop renderers. And I talked to this one guy who was interning at NVIDIA, and he let it slip that NVIDIA was working on something, that he was working on something that was very interesting that he shouldn't have told me. He had mentioned programmable shading, which doesn't mean much to most people, but it's an extremely important technology that essentially enabled everything that we're doing now with AI. Where NVIDIA is today is directly linked to this. Previous to that, the way we made our GPUs, the functions to do the simulation of how light interacts with matter so that we could produce the images inside those video games, the functions were all fixed. We had fixed them into hardware. So there was this big disparity between what you could do in real time in hardware in terms of the quality of the computer graphics versus what I was doing in film and for the very high end rendering that we did for visual effects to make them look really photorealistic. What NVIDIA was about to do is they were making the hardware programmable. So the same kinds of functions that we write in our software renderers that take hours and hours to calculate to produce the images we produce in film would now be possible potentially in hardware, and things that took hours would take milliseconds. So he kind of dropped this with me, and then when NVIDIA called me to interview me because they really wanted me to come work on some secret thing, I actually didn't plan to go work for NVIDIA, but I wanted to find out more about this technology. So I went in and went through the interview panel, and at the end of it, I was kind of in shock. The people I talked to were so brilliant. There was such a diversity of knowledge, things that I didn't know about, and I hadn't been surrounded because I primarily worked in Hollywood, where most people aren't engineers. Most of them are artists or in the creative area. This idea of working at a place where everybody is like me, they're engineers, but they know things that I don't know that I could learn from, and I could potentially be part of developing this new technology, which I believed would be transformative. I thought, okay, maybe I'll come work here for a year or two. And so I joined NVIDIA. They wanted to make me a manager to lead a new team. And the team was to go build a new language. It's called, we called it CG, C for graphics. It was the first shading language to take advantage of this programmable shading. And I told them that I never want to manage people again. I'd already gone through that experience with my own company. And I also told them that I would never live in the Bay Area. I was in Los Angeles at the time, and I wanted to live in New Orleans, where I'm at. Both of those things I failed at miserably. Now I lead a very large team, and this is the second time I'm living in the Bay Area. But I thought I'd be here for a year or two. And then it just turned out to be so amazing being part of this culture on the forefront of developing the technologies that were most important to me. That language I've worked on, CG, was the progenitor of CUDA. We introduced CG by making our hardware programmable for computer graphics. We opened up the possibility of programming it for other types of simulation. And very quickly, people who were paying attention in the scientific community realized that they had these supercomputers available to them in the form of gaming PCs, very cheap supercomputing available. And so they started twisting their simulators, their algorithms to fit our computer graphics pipeline. When we noticed what they were doing, we said, instead of them contorting themselves to make their other physics problems like fluid dynamics and molecular dynamics look like computer graphics problems, let's give them a proper platform that's general and easy to program so that they could take advantage of all of this computing, and that gave birth to CUDA. And so I ended up staying. A few years in, I realized this is going to be the last job I ever have, and I understood that what we were building was far more than a solution for computer graphics, for video games, for workstations. We were building a new kind of computer. this accelerated computer that was going to change everything. Jensen talked about it at the time. You can go back to his keynotes and all the things we said in the press back in 2006, 2007, when we introduced CUDA. We believed that with Moore's law coming to an end, that this was going to be the only way innovation could continue, because at the heart of all innovation is computing. And at the heart of that was this belief that we're going to get an exponential increase in the amount of computing available to us. This was going to be the only way we're going to get it. And he predicted that someday, some grad student's going to figure out how to take advantage of all this computing and make a killer app. So that happened in 2012 with the ImageNet competition. AlexNet was introduced, and it was two grad students and their professor, Jeff Hinton, who established this new form of software development called machine learning or AI on our GPUs at this grand scale. And the rest of that is history. You guys know where we're at now, but I've been a part of that ride, and we didn't know exactly where it was going to go, but I felt, and all the others that were here with me throughout this time, which there are many of at NVIDIA, we understood that we were building something special, and this was going to either we were going to completely change the world and become the most important company in the world, or we were going to die. It was going to be one or the other. And so those of us that stayed bet that we weren't going to die, and we were going to change the world, and that's kind of happened now. It may look surprising to you and to others, like NVIDIA came out of nowhere, but it's not that surprising to those of us that have been here.
So you start in around 7 years after the company was created. So the company was still in its inception. Well, at least for actually the startup world that we have now is nothing, or is a lot, 7 years. But I would like just to touch, so from you starting, like you mentioned, you touch from not wanting to manage people to become one of the key people within the organization, and as well, probably a lot of things you're doing are right now in the epicenter of the innovation of NVIDIA. So tell us a bit about that 22 years journey and some ups and downs, and as well, because I think one of the challenges we have nowadays is that we talk about technology and innovation on the velocity. And at the end of the day, there's still a sense of you have to keep going and creating something solid, like a good tree has strong roots. And I think that's why NVIDIA is so strong, because you guys created something so amazing that the roots are so strong, but it didn't go and start getting fruits immediately, like a lot of startups that appear, they explode, and they explode in all different ways. A bit of that angle from your angle, besides as one of the key people that have been in the organization since this time.
Yeah, I think it's very surprising to others, and it's a unique, where we're at and how we got here, I think is very unique to NVIDIA. And what's unique about it is ultimately Jensen. He has established this culture, and he put us down this path and placed these bets that I don't think anybody else has ever done in quite the same way. The big challenge throughout this period of time, you can go back to when we introduced CUDA in 2006 and go look at our stock price for about 10 years. It was either flat or declining. By introducing CUDA, we took a big hit because CUDA didn't help us with our core business. Up until fairly recently, just the last few years, up until a few years ago, our largest business, what paid for everything, was gaming, video games. And when we introduced CUDA, that introduced the cost to our chips. It increased the cost to our R&D. That didn't benefit gaming at all. It was actually a headwind. But the unique thing that we did because of Jensen is we had this first principles belief that Moore's law in its original form was ending, and that exponential increases in computing capabilities is a fundamental driver of all innovation. It's extremely valuable, and we need it as a society. Something has to take its place. And on first principles, we believe that the old way of doing computing with these general purpose computers with CPUs, which was so convenient to write software for, that was going to come to an end. And so something has to replace it. And we believed our model this data parallel model that comes from the kinds of computers we built for computer graphics was the right one for the future. For most algorithms that were going to be important, we also believe that once we provided these computing capabilities, along with enough install base of it, there would be new applications that would emerge that didn't exist before. And so we were willing to invest in this deeply for a long time on this conviction. Most other companies won't or can't do that kind of investment. There's something unique about having a founder CEO who has been with the company this long and has had such a great track record making these kinds of bets. I don't think you could have that situation, with a new CEO or somebody that was hired later. Even if they had a great idea, you need the credibility that a founder CEO like Jensen has, and he was willing to do it. So we invested for a long period of time and just waited. And then when it happened, we were alert. We understood what it meant when machine learning, deep learning, this new kind of AI thing appeared on our platform. And then on first principles, we went all in. We said, what are the things that we're going to need to build to bring about the future? How do we capitalize on this? And the first thing was, well, we have to take these computers that we're building and make them really big. The more, the better. They have to become really large supercomputers that are at the scale of data centers. So we spent the next decade figuring out how to scale up our computing to this. Nobody was asking for it at the time, but we believed it was necessary. And the other thing that we believed is that with this new form of software development, machine learning and AI, there are going to be algorithms that we can now develop, that we've unlocked the ability to develop, that we had previously just kind of given up on. For decades, we've been trying to do computer vision and image classification and many of these algorithms, and computer scientists had failed at it. This was now possible. We had solved image classification. There are many other ones that are going to be possible, and the most valuable ones are going to be the ones that interact with our physical world. Algorithms that perceive the world around us, and algorithms that can manipulate the world around us, essentially robotics algorithms that the promise has always kind of been there, but it's just been out of reach. We believe that was going to be possible. And so what we need to build in order to enable that became interesting to us. And that quickly led us to simulation. We said, if we're going to create AIs that understand and manipulate the world around us, those AIs are going to have to learn from some examples. And where are those examples going to come from? It's hard gathering them from the real world. So we should turn the real world into software, into a computing problem. Once we have it inside a computer, that data can then feed our AI systems, and we can eventually solve that. So this is what we've been doing all along, and that's been my journey through NVIDIA. I started from, I was doing visual effects before. I came to NVIDIA to apply the technologies that we use for making photorealistic, high fidelity visual effects, which were essentially simulations to produce these images, to making them real time so that we could do them interactively, essentially inside video games. And then once we unlocked the ability to create these algorithms, these AI algorithms, I switched over to essentially robotics, because we believe that we can start building robot brains using this technology. And a key element of that is simulation, which we've been doing for video games and visual effects all of those years. And we can now apply those technologies to building the simulators for building things in the real world, especially autonomous agents in the real world.
No, that's fascinating. And I think you probably condensed the last developers of technology and internet in the last 20 years. So you are in the epicenter of the physical, the digital, and as well the how you render physical and digital, and they combine it to create new evolutionary digital sentience or even robotics. And your team leads, or you lead with the team NVIDIA Omniverse. So, and I think for people listening to us, I'll try just to combine in a simple way. So you're running physical simulation and artificial intelligence technologies that are pioneered by NVIDIA, like you just mentioned, to a single platform for creating and simulating physical accurate virtual worlds, which is NVIDIA Omniverse. So this is right now what you lead worldwide. And of course, it's probably the most cutting edge program in terms of technologies. And the NVIDIA Omniverse is a platform of APIs, SDKs, and services that enable developers to easily integrate universal scene description, OpenUSD, and NVIDIA RTX. So I'm not going to all the terminology for people listening to us, but explain this part. First of all, what is NVIDIA Omniverse? Your work in building these amazing new capacities of expanding AI in physics, digital, and as well engineering parts.
Yeah, there's a lot to unpack there, but I think it's possible to kind of reduce it to a simpler form so everyone can understand. I think first we have to explain what we mean by AI. I think that's a pretty broad term. In this context here and the way we think about it, for us AI is simply a new form of software development. Up until the creation of machine learning, deep learning, and this new form of AI, all advanced software, all of the advanced algorithms we were innovating and creating were done in a particular way, the same way since we first started. You would have a really intelligent human who knows about computer science and computers, how they work, kind of envision an algorithm, an idea, and then they would encode it into a program using a text editor and compile it on a fairly small computer into an executable that they could then run. All algorithms up until this point had been developed this way. The problem with this technique was that there's some algorithms we just couldn't figure out how to solve. Image classification was one of them. We had tried for decades and decades to tell the difference, to write an algorithm that could tell the difference between a cat and a dog in an image and do that reliably, and we couldn't do it. What the team at University of Toronto introduced with AlexNet, when they smashed all the other benchmarks in the ImageNet competition on image classification with AlexNet, was a new form of software development. Instead of a human imagining what the algorithm should be and writing it, we instead told the computer, we gave the computer a bunch of examples. We showed it images of cats and dogs and elephants and tractors and airplanes and all these other things. And we said, when you see this image, this is a cat. When you see this one, this is a dog. And we did that enough times that the computer wrote the algorithm. It created a neural network that encoded the equations and the algorithms to do this. Fundamentally, this is a new way of developing software. And instead of us explicitly telling the computer what to do, we show it examples of what we would like it to do, and it figures out, it writes the software for us. Now, what do you need to develop this software? There are two essential inputs into the system. One is you need a lot of computing. The other is the data, the examples that we provided. These two combined can then write the software for us. And so our insight when we looked at this was that we have to go develop these two things, both the computers and the source of data. The first, for at least the algorithms that are we think are interesting and valuable. The first one we set about building larger and larger computers. We built our DGL computer. The first one was delivered to OpenAI in 2017, I think, whenever that was. And we are where we are now, the largest company in the world, because we're selling lots of that computer. The other one, the source of data, well, that's a tricky one. Where do you get all of this data to go train these AIs? Now, the amazing AIs we have today, ChatGPT, Claude, Llama, all these large language models based on the transformer architecture, they're doing all these amazing things, but they've been trained largely on data that's abstract, the stuff that's easy to digitize, that's already in information form. It's what's readily available on the internet. They've been trained from text and language, essentially. That's why they're called large language models. These are really, really valuable models, but we believe that the most valuable AIs are going to be ones that deal with the physical world, the world of atoms around us, not just the world of information. And that data, the examples that we need to go train those AIs, that's not readily available on the internet or anywhere. You can't just go get millions and millions of hours of robots driving around in our streets off the internet. You can't get millions of hours of operating a factory or building houses and buildings, and all of this kind of information just doesn't exist there. And so we realized the only way we're going to generate that data, those life experiences for these physical AIs we want to create, is by creating a simulator, by essentially turning the physical world and the world around us into a software problem. Once we can simulate the physical world, we can generate unlimited amount of data. We can do it safely. We can do it with great amounts of diversity. We can do it faster than you could gather this data in the real world, because we're only limited by the amount of compute we have available to us. So almost a decade ago, we decided, let's start building all the simulation technologies necessary to do this. And let's build the computers for this, because we know it's going to come. As soon as the AI thing explodes, the next wave is going to be physical AI. And to enable physical AI, which is essentially robotics, we're going to need these simulators and simulation computers that can represent the real world inside a computer. And so we set about building Omniverse, which is loosely, you can sort of refer to it as kind of an operating system that consists of a bunch of functionality to both assemble virtual worlds that match the real world, as well as simulate them to go build simulations of the real world. By itself, it's not actually a simulator. It's not an application. It's more like an operating system where it has all this functionality, and others can build on top of it or incorporate parts of it into their applications and solutions and technologies. So we work with almost all of the tools providers and simulation developers in the ecosystem to do this. So that's basically what Omniverse is. We believe that the next industrial revolution is on its way now. The next industrial revolution is all about having autonomous agents inside the real world, in the physical world around us, doing things alongside us, doing things that we as humans possibly can't do. These are robots. They're robotic systems that will operate and participate in our factories, in our warehouses and supply chains, in transportation, in operating our cities and our buildings, and so on. And in order to build that, we need these two fundamental technologies. We need AI, and we need simulation to create the right AIs.
So this is a masterclass, and thank you so much for putting it so simple. And for people listening to us, I know that what you're talking here for you and me is quite passionate, but the rest of the world is probably getting a hard time to understand. For instance, I'm having a talk with the government and the prime minister in a couple of days, and presenting this to entire economies is not a simple task. Jensen is amazing doing that work, and you are as well, because you guys are fantastic storytelling. So I want to touch three things, but before, let's start with one. So when you look at what you just described in the Omniverse, and for people listening to us, I always try to go and I can think very large like you, and I think we can talk about the fifth industrial revolution and everything we're going to have with AGI. But before that, so in terms of the Omniverse, a lot of things, and you touched that. So you have smart cities applications, autonomous vehicle simulation, configurator development, reinforcement learning, synthetic data generation, virtual facility, which is virtual factories that can be completely automated. It's already working. You have the partnership with Siemens and a lot of other corporations. So from this, I would like to just, before we go to the future, and I have a couple of questions on the future, and that excites me as well more because I'm a futurist as well. So how do you see this in the real world that we are now? Because we are in a very paradox. In one hand, we have the amazing technologies, but we have a working force that is still not digitalized. And as well a big challenge in digital basic transformation. And I always try to do this because sometimes I think like you in the future, and I'm building this kind of technologies myself, but then I have the reality of the world. So how do you see the bridge between, and I'm sure that you have as well, and you guys are amazing to do this with real cases, but like one case study where you saw a massive positive, I don't want to talk about the dystopians, there's enough people talking about that, but a positive case where you saw a massive, I would say, social impact that you see that can actually impact on the present. And like you said, in 20 years, we can do amazing things. I would like to hear that from you as someone that is building the foundations of the next world.
The way we think about it, building complex things, engineering very complex systems, it's very difficult because it requires many people to work in parallel and work together and synchronize their work to build that system. You see this, some of the most complex things we build are software. If you were to look at something like an operating system like Linux or Windows, the number of lines of code is staggering. The amount of, if you had every bit of logic, every instruction in that code represented as a piece of, gear in a piece of clockwork, I don't know how large it would be, but it would probably be larger than the size of our planet. There's no way to really understand what the ramifications are when you make a change to such a system. You can change one line of code, and the effects of that, the bugs you might introduce or the behavior, what it can change, no human can reason about. You can't tell just by changing that one line of code what might break or what might change. You have to go try it. And so the way we deal with this kind of complexity in building these systems where thousands of people are modifying lines of code to this big code base and keeping it stable and robust and being able to move quickly at the speed of software development is by building these CI/CD systems where we essentially test how that software is going to be used as we're developing it, as people are contributing changes to it. We test it continuously and essentially simulate how that software will be used in the real world, so that by the time we release it, we are confident that it's going to work and work well. This is the only way we figured out how to get thousands of people contributing to complex things, complex systems that don't fit in any one of those humans' brains. We do that by essentially simulating how it's going to be used. We've been doing that in how we design our chips from the very beginning at NVIDIA. Before we tape out a chip, before we send the design to TSMC to go be fabricated, and before it comes back to us, we're confident that the design is going to work, that it's going to be able to run all of the software that's been developed for the last few decades on our platforms. It's going to be backwards compatible, and everything's going to work great because we have supercomputers that are simulating our chip design as our chip designers are working on it. We're confident that through the simulation, the design is good and it works. The moment it comes back, this thing that consists of billions and billions of transistors, so complex, no one person could understand it on its own. It boots up immediately when it comes back every single time. It's mind-blowing. We believe the same thing, the same way of designing complex systems has to be applied to everything that's engineered. Every product that we build, whether it's a smartphone, a car, or whether it's the machines that build those products, the factories that build our cars, the factories that build our electronics and our computers, our warehouses, our cities, all of these things are becoming so complex that we no longer can do it the old way. We have to be able to engineer these systems, design them, and operate them in the same way we deal with complex systems like our software and our computers. But the problem is that the real world, things that are in the physical world, are even harder for us to simulate. We haven't had the technologies necessary to simulate these things to an accuracy level where we can try them out. We can simulate many variants, our changes to that product or that world before we go build it. This is what we're focusing on. We're essentially trying to take the real world with our new computing technologies that we've developed, these new kinds of computers, and with AI, make things that were impossible to simulate before possible, so that we could now design these complex systems, things like our cities, our factories, our warehouses, design them well, design them efficiently, make them so that they're safer, so that they're sustainable. And then as we operate them and we want to modify them and evolve them, we can make changes to them and be confident that those changes that we do in the physical world are going to work, because we tested millions of variations of that in the virtual world first. That's the fundamental thing that we're doing. What's been missing has been the computational capabilities. This is computationally very expensive, so NVIDIA builds computers that are increasing in capability at super Moore's law, so that's part of it. We didn't have a line of sight to building the algorithms that were necessary to do these simulations before, but with the creation of modern AI and machine learning, we now have that. We believe that essentially any algorithms we need to simulate these worlds are now possible to go develop because we have this core technology. And then the third thing that's been missing is a way to represent the physical world with all of its layers of complexity in a form that we could then run a simulator on. So if I want to simulate something like a factory, I need to bring in all of the aspects of that factory into one data model, one representation with all of the layers of information. I need to have the building, the conveyor systems, the robots, the cameras and sensors that are sensing everything going on in the factory, the humans inside the factory, every aspect of it, and every aspect, physical aspect, all of the properties related to them, how they react to visible light, essentially what a camera would see, to LiDAR, to the Newtonian physics, fluid dynamics, all of the things going on in there. We need to be able to represent all of that. And up until recently, there was no way to combine all of this information into one model, one common way of representing it. We have simulators and tools to go design different aspects of all of the things I described in that factory, but all this information was spread in different islands, in different data formats, in different tools and different potential proprietary ecosystems. So for almost a decade now, we've been working towards standardizing this representation, bringing all of these disparate sources of data together from CAD tools, from simulation tools, and also from capturing from the real world through cameras and other types of sensors, putting it all together into one holistic representation in a standard called OpenUSD, Universal Scene Description. Last year, we formed the Alliance of OpenUSD. Its founding members are Pixar, who invented OpenUSD to begin with, Pixar Disney, Apple, which has had OpenUSD in its devices, in Safari and the web browser now for 5+ years. The Vision OS is built on OpenUSD for representing these worlds. Adobe, Autodesk, and NVIDIA, we were the 5 founding members. And since then, we have 30+ other companies that have joined, many or most of them coming from industry, companies like Siemens, Trimble, and even companies that build things in the physical world, like IKEA and Lowe's have joined. So we finally have a line of sight to representing the physical world. You combine that with the AI technologies and the computing technologies that we're building, the possibility of doing full, complete, rich simulations of things in the physical world fast enough so that it can be useful to us is now there. We finally have the basic capabilities of doing this. And we believe that this is necessary for us to build all of the physical things that we need to build in the world around us.
Now, that's first of all, congratulations. This is a massive achievement. And of course, it's changing the face of the physical, digital, like a lot of people mention. and as well as creating a lot of new patterns of business, new directions that can be explored, new jobs, new opportunities. So I want to now a bit more on the futuristic side, and I know that I passed 1 hour, so probably 2, 3 more questions to wrap up. So
I have time.
okay, thank you so much. It's an honor. So one thing, Rev, so when we talk about, you mentioned AI agents, and this, of course, is probably the biggest part because you have to go from the present AI agents and to transform this, like you said, on the physical and digital. So at the moment, we are in a verge. Well, Sam Altman official said that we have artificial general intelligence next year. And as we speak, right now, we're talking about around 2 to 5 billion AI agents that could reach by 2030. And that will be more or less, and some of them will be very basic chatbots for people listening to us. Others will be quite advanced AGI, digital sentience. Whatever you like it or not is happening. Then, of course, I did a kind of an algorithm perspective, and I want to hear your opinion as you are building this as well. So I use an AI to build a system of prediction of the number of AI agents we're going to have by 2030, 2050, and 2100. And this is quite amazing because this is pure data and is not, of course, my direct calculations, but indirectly from my study. So we might reach 2030, 2 to 5 billion, 2050, bearing a 35% growth rate, could get by 500 to 1 trillion AI agents, and by 2100, over 100 trillion. So I want just, how are you going to be dealing? Because do you see this? And of course, you are part of films like X-Men that talk about a different version of the world, and of course, where different powers. And I want to, for people listening to us, because of course, we have to look from an engineering perspective. I'm completely with you. This will not stop, and you just need to get the physical and the digital to work together and create new revenue streams, new engineering models. And as well, this will be enabling extension of life, a lot of different things. But we have a lot of challenges as humans, okay? So, and I know that you are as well in storytelling through your work with special effects and entertainment. So how do you see this narrative, and especially what you're building and the engineering side, on the narrative side of human, and as well on the computing capacity? And sorry, it's a big question, but I think what you do is so big that you have big questions, because you need a huge amount of computing power in one end, that you need to create a narrative for people to understand that this is good and this is important. But how we put all of this together, it's like an orchestra and the maestro. You are one of the maestros, so I just want to provoke in a good way.
So obviously, we believe computing is important, and I think the world believes this as well. I mean, that's why if you look at the top 10 or 20 companies by market cap today in the world, almost all of them are tech companies that are specifically in computing technology. But if you look at the market for information technology worldwide, yearly, that's about $2 to $5 trillion, depending on how you measure it. $2 to $5 trillion, which is a lot of money. I mean, that's a really, really huge market. And that's largely where NVIDIA and the other technology computing companies play within this market. But if you take everything else that's not computing, things that are industries related to the physical world around us, that's more than $100 trillion in markets. Transportation, manufacturing, pharmaceuticals, anything dealing with the physical world around us is many times more valuable than the information world. So that's an interesting insight there. You go, wow, we talk about tech all of the time and computing and how valuable it is and how it's the future. But actually, where most of our money is spent is in things that have nothing to do with computing. It's in moving atoms around, essentially, in one form or the other. If you go to a factory today, just pick one random one of the tens of thousands or hundreds of thousands of factories there are in the world. Chances are that the factory you go into will look no different than the factories from 50 years ago. They haven't changed that much, which is kind of surprising. You would think with all of the innovation and computing technologies we've invented over the last 50 years, they should be completely transformed. But somebody, if they time traveled from 50 years ago and came into this world, would be able to recognize everything around them. It would be natural. We've applied some computing technology to the operations of our factories and supply chains and stuff, but in a very limited capacity. We've only applied it to the things that are easy to digitize, the information that's already there, ERP systems and whatever is naturally digitizable. The AIs we're building today, they're amazing, but they're limited to the information that's already been digitized. They're limited to the information that we have on the internet, what humans have constructed. I believe that to really unlock the value of computing and to really benefit from that as a society, we have to figure out how to apply all of this computing to the things inside the physical world. I think we speak with our wallets. If we're putting $100 trillion into the physical world versus $5 trillion into the world of information, I think that essentially tells you what humans find valuable here. So in order to benefit from all of this computing, we have to figure out how to apply it there. What we are focusing on with simulation, what we're trying to do here is essentially make a bridge. We're trying to turn the physical world into a computing problem so that we can turn all of our problems, all the things we're trying to do into the physical worlds, essentially into a software problem. So we could move at the speed of software, at the speed and efficiency of software. Now, what is that going to be worth? I don't know. I don't think anybody can really predict what's going to happen. You know, how valuable such technology is going to be 20, 30 years from now, how many agents, how many robots we're going to have out there. To me, it feels very much like the early days of the internet. I had found the internet actually really early, pre-web. I found it so I could find out more about computer graphics in the late 80s. And then the web happened, and all of a sudden everybody was trying to join this thing. And there was a lot of discussion about how valuable is the internet going to be? What are going to be the applications on the internet? Nobody accurately predicted where we are now, but I think it's unquestionably, we think the internet has changed everything and it's created a lot of value. That's for sure. There's a lot of issues maybe we've also created, but it's created a lot of value. This new technology, AI, the ability to manufacture intelligence, and then combining that with the application of that intelligence to the physical world, I think is even greater than the introduction of the internet. And so the value of that is going to be much greater, and the value creation is going to be much greater. No doubt about that. Exactly how? We can't be sure. So our strategy is to just take it a step at a time. We know it's going to happen. We're not sure exactly what the shape and form of it is going to be 20 years from now, but we're pointing in that direction, and we're building all the technologies necessary to get to the next step, one step at a time.
No, I subscribe, and it's a key element. So I have one question I want to touch, and then I come back to Omniverse to finish. So how do you see AGI? Because you are partly building it. So I know that there's a lot of discussions. It's a massive conversation that can go for hours. But just a bit purely from an engineering perspective and from someone that is creating the foundations for that. So I know that there's a dystopian vision. There's a less dystopian. For me, I see it as an evolution of humanity in a lot of ways, for good and for bad. And I have brought some philosophers to this channel, like Nick Bostrom. That was the first one that wrote a super intelligent book. But I want your opinion as one of the foundational engineers of this new world we're building on the case of augmented general intelligence for people listening to us.
I'm glad you reference the philosophers and you're bringing them on board, because I think that question is really more the realm of philosophers than it is the realm of engineers. We don't even have a good definition of what intelligence is, let alone general intelligence. I'm not sure how to define that. You know, it wasn't that long ago we said the Turing test was the ultimate test for general intelligence. We passed that a while ago, and it seems like that's just not a thing anymore. So I don't know how to talk about something like that that's not really well defined. What's true, though, is that for a long time now, we've had specific intelligence, not general intelligence, but specific intelligence that's superhuman. You know, when we first solved the image classification problem, starting with AlexNet, it wasn't quite superhuman, but it didn't take long. Within a year and a half or so, there were image classifiers that could distinguish subtle differences between breeds of dogs better than any human human could do. We've reached super intelligence in these specific forms in many specific areas. We can transcribe audio, we can do translation of languages, we can do all of these things that were considered only human before, and now we're superhuman in them. This is what actually excites me. The fact that we have forms of intelligence that are specific but superhuman. As an engineer, it excites me because I start asking, what can we do with these things to make our life as humans better? And so what we're focused on building is the intelligences, the AIs that we can cobble together into systems. We can assemble them together into systems that enhance our human life, and specifically our life, not on the internet, but in the physical world around us. Whether or not we will define what general intelligence is in our lifetimes and whether we'll reach that, I don't know. I can't really tell you. So far, it seems we haven't done a very good job at even defining it. So I'll leave that to the philosophers to discuss. But I think we should talk a bit more about these amazing capabilities we now already have that we haven't made use of yet. We built the capabilities of these new types of algorithms, new AIs, new types of intelligence that we haven't made use of yet. For robotics, where I'm largely focused now, we've been dreaming of robots that could do relatively simple things for humans for a long time. To fold clothes, to reliably screw in a screw without programming the thing in a specific way for weeks or months. All of these capabilities, like we've been dreaming about them for decades, and now we actually have the fundamental technologies to do it. So a lot of this stuff that was just a dream, or maybe it was science for a while there, they've now become engineering and systems integration problems. So that's where we're focused. We're focused on the pragmatic. What can we do with these amazing new superpowers we've now created? And let's go put them to good use.
I completely subscribe. So last one, I know that we pass it, but so one of the things in the website of NVIDIA Omniverse is the infrastructure. And you just touched robotics, which was my last question. So we have right now kind of 5 or 6 mainstream robotics. I interviewed Sophia the robot actually in this program of the founders, which was probably one of the first non kind of engineer mass market robot to have some maturity, and as well I interview other robots. So at the moment we're able to do something much more advanced. Tesla is launching, of course, their super robots, and there's a lot of robots already using, for instance, with Amazon. You guys have partnerships with all the these corporations. So how do you see this short-term robotic revolution and what Omniverse is doing in terms of infrastructure, engineering, and as well the capacities for enterprise supported versions?
Very good question. We've had the concept of robots in science fiction for a very, very long time. Everybody's grown up. Everybody on Earth now has grown up with an idea of what a robot is. Generally, when we talk about robots, if I say the word robot, probably the image that enters your mind is something that's a humanoid type of robot, like C-3PO is what shows up in your mind. But that's one form of robots. The term robot is actually, it applies to a much more general set of things. What is a robot? Our definition of a robot or a robotic system is essentially an autonomous agent that operates in the physical world. A robot does 3 things. It perceives the world. It essentially ingests the world through sensors and makes sense of what it's seeing. It then makes decisions and plans. It reasons about what it's seeing, and then it actuates. It does something to modify the world outside of it. It manipulates something. It moves inside that world, or does something that changes the world. And it does this in a loop. So it perceives, reasons, acts, and that act changes things, so it has to perceive again and reason and act. By this definition, many things are robots. A self-driving car is a robot. It perceives, it reasons, and it acts. Buildings are potentially robots. I always like to use this example in our NVIDIA headquarters. When you enter our reception area, there's these turnstiles and they have sensors, they have cameras there. When you walk up to it, it perceives you and then it makes a decision if it's going to let you enter or not. It knows who I am. It can classify me and find me in a database and say that I have security access. So it actuates and it opens the turnstiles and lets me through. These robotic systems are increasing everywhere. Now, why haven't we had more robots around all these years? That's a good question to ask. We've had the dream of it. People have been trying to build them. The reason why we haven't really had them at scale is because building a robot brain has been too hard. Making them robust so that they can deal with all of the different unexpected situations in the real world has been really, really hard. And even if you could program them, it took so much engineering effort to program them to do those specific things, it wasn't worth it. So we've had very limited applications of robotics throughout the last few decades. Largely, they've just been in automotive factories because that's where you could afford the capital cost of programming robots to do one specific action over and over again for years at a time and make it worthwhile. You don't see them in essentially any other factories or in any other types of manufacturing because they don't have those same conditions that the automotive industry has. Now we finally have the ability to create good robot brains and make them potentially cheaply. The ChatGPT moment unlocked this in the imaginations in almost everyone. We finally understood that we can create a general enough intelligence to reason about many things, and if you could apply that to the physical world around us, essentially we have the core technology to create a useful robot brain. So once you realize that, the next question is, well, what types of robots should we build next? Which ones should we go focus on? You might think, well, we have robot arms in factories, and we have self-driving cars, and we have mobile robots that can shuffle around inside these factories and whatever. Maybe we should be focusing on all of those and building those out more. But if you take a step back and go, this new AI technology allows us to create a more general purpose kind of brain. What's the right robot that could use a general purpose brain that's not built for a specific purpose? If you look around you and you look around all the places you go to, you notice that the spaces that we've built are built for humans. They're built for us to go operate in. Retail stores, factories, sidewalks, our homes, our kitchens, all these spaces are configured for beings that are roughly our size, our height. They have 2 arms, 2 legs. They can navigate stairs and ramps and those kinds of things. And humans can do many different things. They're kind of general purpose. So what's the most useful application or most useful body we can give to a general purpose robot brain? It turns out that that's probably humanoids, because we can take our existing spaces and place a humanoid body in there and they can go do useful things. So what we've seen since ChatGPT is there's been this acceleration and kind of explosion in R&D investment in humanoid robots. You mentioned Tesla. They're one of them, but there's many other companies also doing this. It totally makes sense because now we have the technology to make a more general purpose robot brain. And the most useful general purpose robots are going to have roughly the human form because we can place them inside human spaces. They're going to be in our factories and warehouses and hospitals and retail stores and so on. So I think that's going to be the next thing. We probably have had the technology to build the mechanical, electrical part of the physical part of these humanoid robots, but there was no point in advancing those technologies because we didn't have the brain to unlock their capabilities. But now we have the capability of building a brain, and so we're seeing this acceleration. That's going to change everything. They're going to be the first robots we see deployed at scale because it's going to take a while for us to reconfigure many of these spaces to be right for most optimal for specific robots. Eventually, we'll see lights out factories and warehouses where humans don't have to operate in those spaces, and we can have more optimal robots for those spaces.
but most spaces are created for humans. So humanoid robots are going to be the first one.
Wow, this opens another podcast just about robotics, and it's one area that I'm very passionate. I actually interviewed 2 robots in this podcast, and actually was quite amazing experience. Actually, one of them was 4 years ago, so it shows what 4 years can do, and as well the velocity. So I think I'll wrap up for you because I want my audience to digest this. But definitely, one thing, Reb, I would love to do is a take two. And I think the take two will go a bit bigger, but we go more technical for the people that are excited because there's a lot of things to digest. It's been a fantastic, mind-blowing interview, and I'm very excited, I have to say, because you touched the history of the last 40 years of technology. Like you said, we start the interview talking about 1993. We are in 2024, so it's 41 years. Exactly. And in these 41 years, of course, humanity changed. But you touch a very important thing is that the technology changed massive, but our physical world didn't change much. And I think that's probably a great podcast. What can you do to change that physical world and create a better non-dystopian narrative, but as well a practical level, which I think is what you guys are doing. And that's why you achieve the revenues you did. So, Reb, it's been an honor and a pleasure. A lot of more questions. Definitely, I'll work with you and the team for the take two, and I will be much more for people listening to us. I want people to digest all of these different things. We put this divided by parts. Well, there's a lot of more questions that come straight away to my mind, but for the sake of 1 hour and a half, we'll work right now here, and then we'll do a second take. So thank you so much.